Okay. Registrazione, let's hope so. Okay, so let me check because there was Cinzia coming and Cinzia is not here. Perhaps we can start. So, no, Cinzia is not. All right, so this is the second of our meetings. And today I want to go more in detail about the algorithm. Okay, just now I am upset. Why it was doing happily oh, okay, now it's doing it, sorry. Right. So first of all, let me quickly remind you what we said last time. And what is our purpose? I'm explaining you this algorithm of deep learning that is mainly used, not only used, but mainly used for visual recognition. So the problem that this algorithm is facing is the following. I show you some photos, some pictures. They belong to, say, 10 categories, whatever. So there is a fixed number of categories. And then the algorithm will tell me what this picture represents. So for example, in this slide, taken from the Stanford course, the picture represents a horse. And indeed, after some layers, what this means, we come back later, the algorithm will tell me, you know, the probability of being a horse, it's way more than the rest, and then labels horse. Okay, that's the, as I said last time, convolutional neural networks, that's another name for deep learning, convolutional neural network. They're used for other things. I personally use them also for other purposes, but mainly the reason they became really famous and the main use, I would say, is this. Recognizing images and labeling them. That is what they do. And of course, guys, if you have any questions, do stop me anytime. I mean, we're here for that, not for me just going through slides. Okay, so can you help me how to see the full slide and not, I mean, how do I get rid of this? We don't know. Okay, very annoying. Ah, some people are joining us. Sorry, guys, I need to let them in. Great. Okay. So as I was saying, we have some ingredients for deep learning. And as we will see in our next lecture, because this lecture is deep learning, next lecture we do geometric deep learning, we have the same structure. So we have a score function. So you show me an image, the score function gives a score for each category. So for example, here we have an image. This is the input image. And then we have score like cat, dog, sheep, 3 categories. And this score function will spit out a number for each category. This is not a probability, it just gives me a number. For example, here, this number is obtained by multiplying the weight matrix times this xi, that's the image. It is stretched in a column of numbers. And then we add a bias, we don't care what it is, not so important, and gives the score. Notice that no matter how you obtain the score, you have weights. The weights are the same for all images. So you have this weight matrix, in this case it's a matrix, it can be something more complicated, still it will be matrices in some sense. You multiply matrix and vector, get a score, and that matrix is always the same. Then you have the loss function. So these are 3 main ingredients. The loss function measures the error. I'm putting here the loss function that is called the cross entropy. It doesn't matter. You can use cross entropy, which is really popular, but we will go into it very careful. But I'm saying you have a measure of how much your error is. For example, in this case, you see right here, you have a cat score, which is very low compared to dog score or sheep score. So that shows to you that this is doing a bad job, right? So you want, in this case, to have the loss function to be big, saying, oh, you made a big error. You want the loss to be 0 when you're not making any error. You're catching everything right. And of course, the matrix W is always the same. So you imagine you are changing the weights in such a way that you try to get the least possible error. And then this optimizer. How do you perform this operation of minimizing the loss? I put the, the quotation because that's not really minimum. We discussed this last time. I'm going to come back to this. So you try to move in the gradient. See, if you forget this word, the stochastic that I write here. So at a point, you try to go in the opposite of the gradient. By calculus, we know that this is the direction where it is the maximum loss, right? You go down. This is the gradient. Of course, it doesn't guarantee you that you're going towards a minimum. There is no reason. Perhaps you're going to a local minimum and then there is like a much lower far, but this is the game. How you get around it is that you do this game of the stochastic. So you are not considering all the loss consisting, so you are showing it all the images, right? Then you say, oh, I have like, I don't know, 10,000 images. I compute the loss for each image and I sum them up. You may average by the number of images. It's not such a big deal. So that's a constant. So that would be reasonable. No, you do the gradient to a little piece of it. You pick up 32 images among 10,000 and you compute the gradient for just that piece of the loss. And of course, there is no reason why this is giving you the direction of the minimum. No, there is no reason. But what happens is that the system, so the weights will evolve in a very stochastic way, meaning that there will be a lot of noise when they move, right? So even if your loss function would be convex, which is non-convex, but suppose that is convex, then instead of going down like that, it will go down like this, right? So it will take a different direction. Are these three main ingredients really clear? Do we have questions? Yes, no? Because we are going to discuss in detail each of them. In particular, I want to speak about the loss, which is interesting to me. And of course, the stochasticals. Okay, I thought I could move down, but no. I now get very upset with the system. Guys, do you have suggestions how to go down?
Probably you have to click on the page and down page with a keyboard. No, it's not
the computer working. Is now not obeying to any of my
on the screen. The screen is a touch screen. Try to the.
Okay. But the mouse is moving. No, it did it. It moved. Okay, it moved. Which I'm sorry, guys. I just right. Okay. So let me see. Okay, now it is doing. Okay, so we speak about these three ingredients later on. Let me explain the training. In fact, we can see the title of this slide is training. So how is the training working? Remember that our algorithm is like a little child. So like you are teaching it by example. So oh, this is a dog, this is a cat, this is an elephant, and the child learns, okay? So what you do, you proceed the following way. For example, I'm taking the data set CIFAR10 that consists of 60,000, I think, images in 10 categories: cat, dogs, trucks, airplanes, okay? You take 80% data for your training, 10% of validation, 10% as test, and test you perform once. You don't mix this. So you train your algorithm, and the word training, the learning process is where you determine the weights. You know, this W we saw before, you know, this matrix of W, that's where you learn them, okay? So at the beginning, your weights are given randomly, just any number, the loss is big. Then you go down, the loss becomes smaller, and you determine your parameters. That's the idea. By many iterations with the stochastic gradient descent. Then there is the phase of validation. So you put 80% of your data aside And with the 10% of data, you do validation. What does it mean? It means that you are trying to change what are called the hyperparameters. That is, perhaps the loss function you chose, that's not so good. You try a different loss function. Cross entropy, you take another one, the SVM, support vector machine, whatever. Or perhaps you have the layer and you use these 10% images to make these little changes. And these things that I'm telling you, learning rate, number of layers, and so on, are called the hyperparameters. And then you may train again to see how it is going. And then the test. Once you think you got the best that you can, you test once. Don't mix test with training. And before you think, oh, come on, obviously I shouldn't mix the two. I've done it many times. It's an error you can incur with, okay? So this testing is like sacred and stays away. Happiness for my description. Are we understanding what's going on? Yes, please, please. Yes. Yes, yes. So you decide, so you are, I have to explain myself. Okay, how does it work? You train, and then you're like, oh, great. I do 80% of accuracy where? On the 10% validation. So the test does not exist. You took your test, you put it away. Then you say, oh, you know what? Why don't I change? I add a layer. You retrain, and then you test on the validation again. And you discover, oh, it is 75. No, that's not a good idea. Let's take away a layer and you train again. And then, so the validation is your test many times. You test your algorithm to check how it is going, right? It's a big temptation to test. Ciao, Cinzia. Don't worry, we've been chatting. No math yet. So the thing is that it is very tempting to use the test to do the test. But no, that will be a very wrong thing to do. Because then you would adapt too much to the, so when it sees new samples, you won't be able to perform well. We're going to see what happens if you make a mistake like that, okay? And then every time you do the accuracy, which is the percentage of what is an accurate prediction on the test or on the validation, whatever. So this is where, how you say, oh, I got right, I don't know, 9,000 over 10,000, it means you have 90%. Okay, that's it. Very simple. I don't know if this is. It is recorded. This time I remember, though I'm not 100% sure I'm doing, says, metti in pausa la registrazione. What do you guys say? I am recording. Let's hope so. Computer is putting myself really at try. And now it doesn't work anymore. Why? It hates us. It's not going down. It's not obeying. Perhaps it's just very slow in doing it. Okay, I am... what did I do last time that worked? Ah, you are right. That's how it works. Right. Okay, so this is the learning process. I am sorry because the label is... So the first step in the learning process, you compute the score of the image in the training set, okay? So you compute this matrix times the image, and that's a score. And the weights are initialized randomly. And then you compute the loss. This takes, I think, 1 and 2, take the name of forward pass. I know the computer science people call it forward pass. I'm not sure why. It's because I think you are giving the input to the function and the function gives you the output. I have no idea why they, do you know what they call it for? You don't know, great. When you see forward pass, it means compute the loss with the training. And then you do the stochastic gradient method. And when you do the gradient, they use this name backpropagation. And for us, mathematicians, that's the chain rule. okay? You know what the chain rule is? You have a function, you know, the loss is a real function, depending on many parameters. So obviously, when you compute the gradient, I mean, you are doing, if a parameter depends on another parameter, do I have to explain what the chain rule is? They call it back propagation. So remember, whenever you see the word forward pass, it says plug in the loss. When you see the word back propagation, it means the chain rule. And it makes me smile because why would you call it back propagation? There is a reason for it. And I think they're so proud of it because they have a very clever way to compute it. That's the point. They have a fast and clever way to compute the chain rule. That's the reason. But suppose that you, I mean, you don't need to know. And if you try to read what it is, it's very complicated, very, so don't read it. And then you update the weights. So you understand, first you compute the score, then you feed the score to the loss, determine how bad you did. And then you do the stochastic gradient going towards the minimum of the loss and update the weights. Go back and repeat, 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 repeat many times, many times. How many times? You repeat it 150, 200 epochs. So, for example, one epoch, I do this, for example, in Shifar 10, if you decide to take 32 images at a time, an epoch means that you do 40,000 divided by 32 times, okay? So many times, so about over 1,000 times. That's one epoch, and you do 150. And before you think, oh, it's a computer, will do it really fast. No, it won't do it really fast because it depends on how many parameters you have, right? Because you have a huge number of parameters it has to compute, and it has to do the gradient. There is a function called the autograd. It will do the gradient for you, but with the back propagation. So like, you will do it with the hands-on thing. You can actually watch while he's doing it. So it takes time. Even for baby example, it will take time. And if you're looking at real life pictures, we're gonna show to you, it can take a day to do the training. So I'm just telling you that. So the deep learning, it's very costly when you train it. So it takes days perhaps to train, but it is very fast when you need it. Because once the weights are learned, we call it the model, right? Suppose you learn the weights, you're really happy, it does great. Great, you have your child trained, and now you ask the child, what is that? And the child says, oh, that's an elephant. What is that? Oh, that's a dog. It will do it immediately, right? So it takes a long time to learn, very short time to tell you the answer, okay? So that's why it is a very effective with respect to what was before. Do we get the learning process, how it goes? Yes? Happy? Okay, sort of. Cinzia, I know you arrived late. Okay, but don't worry because then we will, the subject is, we go through the description of the deep learning, and now we go into math. When it is time that we're going to math, you catch up again, don't worry. Okay, so here I'm showing you the behavior of the loss in epoch. So in this graph right here on the, I took it from the Fei course, you can see the loss function. And as you can realize, see the red graph, it goes down, you see, in epoch. And that's what it should do, right? You hope that with the passing of time, right? Epoch is time, remember, it's the iteration that you do. The learning rate goes down. Sorry, the loss goes down. Now you can see the four graph, what are they? It shows to you the behavior of the loss with respect to the learning rate. And by the way, here you see the loss, the real loss in epoch, right? This one. And I will show you also another graph. Why it is so spiky? Because of the stochasticity, right? So the loss doesn't go only down. It will go up and down because God knows where the gradient is taking you. 32 image here, 32 image there, who knows? That's why it is this. So on the right, there is the real loss function. And on the left, there is like a pictorial image. So what happens here is that when you have a very high learning rate, what is the learning rate? I hope to be able to go back. So when we do the jump here, the update of the weights, there is this number alpha, we multiply the gradient by. This is called the learning rate. So if you take a huge learning rate, so what happens is this. I know that you can't see me, but so suppose you're going down here, right? So if your learning rate is going like that, then you're missing the point, right? Because the gradient moves on the tangent. So that is you start doing a very bad thing if the learning rate. In fact, look, the loss with high learning rate, the loss is going up. Very wrong. When you take a too low learning rate, you will go down, but you will go down very slowly because you're moving very little, right? Right? That's what it is. It's going. And when you take a high learning rate, that's not good because you may oscillate. That is the problem between the values. So I wanted to also give you this picture because this is what my students did for me in one of our papers. So they call the learning rate, they call it eta here, but it's the alpha before, and it shows you the loss. You see? So what the people do in a real-time algorithm, they will have like 200, 300 epochs with a certain learning rate, and then they cut it. They divide it by 10, and then they do another 250 epochs, and then they cut it by 10, and then it's the recipe, like a cooking recipe. There is no reason why this should be done. So you do the same for deep learning? You have no program with it. Not so much, but she was the one knowledgeable. So do you do this recipe? You cut the learning rate. You do, what is 150, 200? Was you cut. It was already done by somebody else. Ah, that's cheating. But today you will not be allowed to cheat. You will have to do your own, right? And try to see. Exactly, that's what you will do today. Show what happens if you try to change the learning rate. If it is too high, you see this strange behavior where the loss, instead of going down, it will go up. That's not right. So this is the correct way to do this. But of course, I mean, we are past the pioneering days where you had to try. Now we know this is how it works. And then we have the, okay, I cannot read, the validation phase. So what are the hyperparameters? So we call the parameters, the W's, they get into the matrices, right? And then there is things they call hyperparameters, which are the learning rate, how big is your mini batch? Are you taking 32? Are you taking 16 images? Are you, I don't know, multiples of 2, powers of 2, God knows why, I don't know. What is the optimizer? Because we saw the optimizer gradient descent. There is another optimizer called Adam that you certainly use. Use Adam, right? Everybody uses Adam. Why? And you know what Adam is, right? Huh? Yeah, there's something called the nester of momentum. Is built in. Okay, let's not go what Adam is, but Adam is a steroid version of stochastic gradient descent. So it will do a stochastic gradient descent, but there is more into it. And then the net structure. So we spoke about layers. We don't know what a layer is yet, but okay. How many layers are you putting there? How many parameters? How many channels? That's the thing. And then the training, how many epochs and so on. And the weight is like, if you are classifying the CIFAR-10, okay, one of the most famous database, of course, people know what is best. This has been done. But if you have your own data set, for example, I work with a company, Modena, that is producing little wheels for carts, you know, for industrial carts. And sometimes one of these wheels is defective because the plastic that is done has a little defect. So what happens is that they have a camera, they take a picture, and they ask Fioresi, why don't you tell us if the image is right or wrong? Truth is that we have to train with many of these images. And now it's not the CIFAR, right? Because there are some defects which are, you know, okay, and maybe it's only problem of color, and some that are really bad because the plastic is raw. So there it's like, it's really a problem where we have to do this game, right? Because it is never learned. So what I'm trying to tell you is that, if you're doing research on deep learning to understand deep learning, great. But if you're trying to run it, like I sometimes do, for like a concrete problem, then you really have to do this, right? Because no one has faced your problem before. So this is, I'm sure if you work with Bertonia, you're doing this, right? Yeah. You know the process. They were telling me that now they go, it used to be 200 epochs and then cut, now it's 150, people get impatient. How many epochs do you run? You don't know, but you're now one of these people. All right. Okay, now I wanted also in this first part of my talk, talk about the overfitting. We discussed this briefly last time. What is this showing? It's showing the accuracy, right? So training accuracy, validation of accuracy, and so in the training you learn, and then validation you test. Look at that. The accuracy of training is very high, and the blue shows validation accuracy very low. This is very disappointing, right? It shows that your algorithm knows very well the images in the training. So if you show those images that the algorithm has seen, knows them, but doesn't know the new ones. So it adapted to the training very well. This is called overfitting. How do we avoid overfitting? It is really bad in the sense that there are many ways to try to avoid it. Perhaps you have too many parameters, or perhaps you have too few. It really can be anything, or perhaps you need to take a totally different approach. So if your graph of accuracy of the training and accuracy of validation looks like this one, throw away what you have, start all over. And then there is this validation technique, which is called cross-validation. I just tell you because some people do it. It's like you take your training set and you divide it furtherly. So, you know, there is training, there is validation. Says, oh, I don't want to waste some of my data to do validation, because if you have not many data, for example, when you do DNA analysis, DNA is precious, you don't have many. Then you say, okay, I do validation with a piece of the training. So I do training, I don't know, 80%, 20% of validation, and then I divide the training in 5 pieces and I use it as validation rotating. This is a technique that you use when you don't have many samples. Are we understanding? More math will come our way. No, it's not that is better. I personally don't like it, but you do it when you don't have many data available. So this way you are gaining data because you are using the validation to train. What do you pay? You pay that perhaps you get into overfitting like that. So this is a danger, but yes. Now this is the loss we saw last time, and you see this spit. Now we understand better what this spit is, right? Is where overfitting is. So you get a loss which is very low right here in the spit, but that's not where you want to be, because in this way you sort of adapted your loss totally to your data. That is the problem. You want to be in this plateau, wandering right here, and we're trying to understand with my student Michaela, that I hope she's well because she was not well, what is this plateau about, but not so simple. Because when I was talking to LeCun, I had a brief conversation with him, and he would like, one question he asked me as a mathematician, he said, you are a mathematician, how can we determine the region of good parameters? How do you determine it? He was telling me, are we taking a quotient? Because many set of parameters will give us the same accuracy, right? So you pick certain values, gives you accuracy. Other value may be very different, gives you also accuracy, say 98%. So how can we somehow be economic and determine this region, determine equivalence class? I really don't know. This is very difficult to understand what is the good region. Okay, this is all right. So I think I want to go more so questions on this very, what can I say, difficult point. What is a good place to stop for the loss, and what is a good region of the parameters? That is, but we speak more about the region of parameters in a little while. But we are mathematicians. We like it when it's complex, no? We don't like when it's easy. If you, no, very good question. So if you go that you are in the pit and you have training accuracy, which is very good, and validation accuracy, which is bad, right? So this tells you your algorithm. Personally, I would throw it away, but some people try to mend it. Yes, that's what happens. That you get a very good, so the loss is very, very low. Parameters adapted totally to the training. Usually that's it. I personally start again, but some people try to change what they have. It's like when you're trying to draw a picture, right? Suppose you make a mistake, some people just do like me and start again. Some people say, oh, let's scrap a little bit and see. It's a matter of personality. Truth is, you have a lot of work ahead of you. That is a lot of days, perhaps, because it takes days. Okay, so the three main characters, score, loss, optimizer. Let's go into it. Let's try to understand. So I want to concentrate mostly on the loss, but I want to say some words on the other things too. So the score function is obtained through convolutions. We said it last time. So what I plan to do with I will try to explain how these filters are really taken from our way of seeing images. So you see there is this filter which is in yellow. So imagine this is a filter that you put on an image, and this filter right here essentially will say, okay, we extract the number 1 if there is a direction here corresponding to this direction. So you are covering. And then number 0, so it's like a white noise if not. And then you slide this across the image, and you see that what you get to see here, see there is this direction. You see that you highlighted these directions, the ones like that. So you have a darker, right? So you create an image where the direction is 45 degrees is highlighted. That is the point. And then you do it for all directions. Now, the truth is that it's like if you take in a Fourier analysis course, do you have a Fourier? That's really Fourier is doing that when you do convolution. You are sliding your kernel through with your function, whatever. Now, the truth is that this is what people could think to do, say, oh, let's program in such a way. But that's not how deep learning works. Deep learning will learn the filters. That's the scary part of it. You're starting, so your filter is parameters. So you get like a 3x3 matrix of random W's. And then these random W's, by minimizing the loss, will become these things. They become like, they are becoming those. Very strange that you learn that. But this is happening in our brain too. This is exactly what happens. If you are born, you do not have in yourself the capability of recognizing an image. And you learn it as you, as you see things, you learn. In fact, I have 3 children, so I observe how this happens. It's very funny because what they do like this. When they try to grab something, because they don't know yet how to do that, right? So they're learning, really, they're learning like this machine. And then they recognize shapes, right? And this very terrible experiment I told you, they put kitten inside a box that has only vertical direction. When the kitten is out, it doesn't recognize other directions. Essentially, it's very blind. because of that. So it shows that he's learned only the filter of vertical lines. That is. So this is something we saw last time. I don't know, you guys want to see it, I show it again, but I would like to do some more. What do you say? So this convolution. So in your deep learning, what you do, you have an image, and then you create from this image many other images, same image, by these filters. How many? 64. And you do these filters, so one filter is creating one image, another filter, they start randomly, and then they will be adjusted because of the loss, right? So when they do wrong, they change, that is. And it turns out that the filter really become the useful ones. If you look at them, they're really the useful ones. That is, okay. And yeah, so this is showing to you convolutional neural network. And you can see these filters, right? These are real. So if you look at this picture right here, these are the first filters. They detect the directions. And then if you go to low, mid-level features, see they detect, oh, sorry. They detect the curves. They start detecting some more elaborate. For example, if you look at the animal CIFAR10, so to recognize cats, they use angles because of the ears, right? That's actually true. If we look at how do we recognize a cat from a dog? Because the cat has this, well, there are also dogs, they do have it, but much less. So this is how the algorithm. So you have to think, if we go back to the previous picture, this one, the very first picture here, you remember this W? Okay, imagine instead of having W, is this convolution. So you have many matrices, many, and they form one layer. And then you have other matrices to catch up other. So you have several of these, it's really very complex. Cannot do in 1 hour. I want to tell you many things. Ah, you have to, yes. Okay, 1, 2, 3, 5, 1, 2, 3, 30. Yes, indeed. So each filter gives you an image, correct? So you start from an image, and if you decide to have 30 filters, which by the way, it's not very many, usually 64, 128, that's the number, you produce this. And then each of these images new, you do again, you give other filters. So it will multiply suddenly. Imagine you have these little matrices, you have many of them. Very good. So you have 30 images and then you apply 30 filters. Yes, they multiply. They become. AlexNet, which is one of my favorite nets. Perhaps it was the last time, not this. Perhaps I have it here. So it will grow, and then go back to small. So it will start big and then go back to small. But if you try it on your computer, if you have, say, apply these filters and produce it, and then next level you apply again. You do 3 or 4 of this game, your memory is going to, you go out of memory very fast, right? So it is not unusual to have 1 million of parameters. That's like a number which makes sense. The W's, 1 million. I think ResNet, I forget. ResNet is 10 million, something like that. AlexNet is smaller. So you can, for example, NIST, which is the letters, that you can classify like with few thousand parameters. That's okay. But because it's only numbers, right? That's okay. But if you try to, natural images, you need a lot. I should have put here the numbers. I didn't think of them. No. Let's go back. Very good question. But so. Okay, so you have the loss function L, which is the sum of all the images. And then yes, I made a mistake. It's not a mistake. I didn't explain myself correctly. The stochastic gradient is like you sum gradient of 32, loss. So it is the usual gradient. So if you have a function, So you have the loss function is L1 plus L2 plus L 40,000. Okay, you have 40,000 images, right? Perfect. Then you compute the gradient of L. L gives you a number. So L is a function from a certain whatever, a big number of parameters give you R. That's the loss, right? So the gradient of L is DL1, DW1, DL, sorry, DL, DW1, DL, DW2, and so on. So if you have a huge number of parameters, this is the vector Rn. Maybe n is a million, right? So when you do this stochastic gradient, instead of L, you replace it with so L is replaced by L stock, which is L1 plus L2 plus L32. For example, you take the first 32. Or maybe you take 32 randomly, any, okay? But the gradient is the gradient. So it's really the gradient. Yes, exactly. Chosen images. So it's so you replace L with another function, but this other function changes every time. But the gradient is really the true gradient, like derivative, right? So it's not something different. No, but it's a good question because I write the stock. What is it? That is. All right. So. Right. Okay. Yeah, this I put it. I like it. AlexNet. So I just gave you a feeling of what this is, a typical network structure, which I really like it because it's very simple and performs really well. So if you have, for example, I have this problem of the wheels, I think I would start with this one because it's very simple. So you take your input, for example, here is 642, 864. These were images I took from a medical analysis. And then you do a convolution and look at this. You see a 64 here. So you have the three. Three means that you have red, green, blue, right? The channels. And now you get 64. Why 64? Because you are applying the 64 filters. Okay, that is. And then you do again a max pool. Well, max pool is a very stupid thing where you cut in half or maybe cut in 4 the dimension. I know it's crazy, but it works very nicely. So if you have a 4 pixel, you take the max of them. I don't know why this works, but it works great. And then you do convolution again, a max pool and convolution. So you play this game, what, 1, 2, 3, 4, 5 times, 6 times. And then you do the linear. The linear is really like what you think. So you obtain all these images and then you stretch them like, so it is 20, what is it? 26 times 4 times 3, you stretch them in a vector and you apply a matrix. And you do it 3 times. That is. And you spit out, here we had 4 categories. So the output was 4 scores. We were really doing really well with this very simple algorithm. So this is deep learning because you have convolution many times producing all these directions, right? And then you have this linear in the end that gives you this 1, 2, 3, 4 categories. Here 4. For the Schiffer is 10, whatever. So I wanted to show you this. So these are the images that we were, you know, just examining. I just showed to you to tell you the capabilities. These are images of cell. So you take a tissue and you cut it, and this is, I know by looking at it, you have no idea what it is, me too. And so doctors are labeling them, and then we decide, so we train and decide. We did a very, very good accuracy. This is to tell you because people always think cat dogs. No, you can do more than that. It's just a lot. Okay, so perhaps I would stop 5 minutes because I think it's not good to have so many things. And then we start talking about mathematics and I want to describe the loss function. So let me ask also to the audience if there are questions, if you guys want to say something before we go and put some mathematical formulas on the board. So we stop 5 minutes, we start again at 4:30, but I'm open to questions. And at 5, Ferdinando will do the hands-on. 5 or something. Come on, guys, get a coffee, something. It's not good to be listening to slides for 2 hours in a row. That's, the people are falling asleep. Come va? Sei un po' annoiata perché sai tutto, giusto? Eh? Sì, sì, hai portato il... Sì, sì, perfetto, sì. Come ti chiami? Mi sono dimenticata il nome, me l'hai detto, non mi ricordo più. Francesco? Francesco, sì. No, cosa dici? Si capisce? È troppo facile? Perfetto. No, ma adesso... Sì, ma la sessione di Ferdinando ora forse devo mettere in pausa, perché sennò qua sento tutte le chiacchiere, metti in pausa.
Scusi, prof, mi riesce a sentire? Prof?
Ah no, devo condividere però.
Non mi sente.
Vabbè.
Prof, riesce a sentirmi?
Attiva il video e fagli ciao con la mano.
Prof?
Non la fa più.
Vabbè, lo scrivo in chat.
Okay. Right, so I think it's time to start again. So I wanted to speak about, so before when I was showing you the convolutions, so let me quickly go back here. So this network structure is, I give you an image and then all these layers spit out a score, okay? That's a function score. So for each category, you get a number. That's it. You remember? So let me show you from the beginning. We saw this, the very first slide. That's it. Here we put W. Okay, there is more complicated. It's all layers, convolution, blah, 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 whatever. But in the end, at the very bottom of it, you input an image, you get an array here of 3 categories, 10 categories, 100, whatever, of numbers. That's a score, okay? Now, what do you do with the score? You use the loss to evaluate the error. And now we speak about the loss, because that's interesting for a mathematician to understand. Now, I will speak about probability and statistics, which I know very little. So you guys that are here and the guys that listen from, online, you are very welcome to correct me, because for sure I will say something wrong. I am not a probabilist at all. So, okay, so deep learning uses what is called the cross entropy loss. Okay, so first of all, the loss depends on parameters W, and it is the sum on all the images. Okay, great. What is the cross entropy loss? First of all, you have the function called softmax. This function takes score. Okay, let's understand the probability. Yeah, so we understand the thing that is written here, right in the bottom. So you have the probability. So the score gives you. So you have a certain number of categories, spits out a number, I don't know, like 13 minus 4, 142, whatever, right? So spits this out. This you feed to the softmax. What is the softmax doing? So it's producing an array 13, and then you do the sum, 13 plus e to the minus 4 plus e to the 142 plus, you understand what it's doing, right? And then this is the first entry, and then the second entry. So it will produce an array. This array will have numbers like a 0.2, 0.1, whatever, but they will add it to 1. So there will be a probability. So that's a trick, right? You have an array of numbers that are whatever, and then you spit out something that is a probability. So they add. So the softmax gives you the probability, and we call it P. Probability label Y is assigned to X depending on W. I don't like it. I think it's clear what it does, right? That's P. And we call it the empirical probability because it is the one we obtain by our W. Give me a W, I give you this probability. Of course, if I give you a random W, it will be a probability very wrong. It will tell us something is a cat and instead is a truck. Okay, that's the thing. Now, if you try to read this guy, Amari, which I don't know, it's been a trying experience. He's a mathematician, Shunichi Amari, and it's very funny because this guy is an old guy, he's like 70 or 80s, and he's written his life for many, many things. He's written one paper, which is called The Natural Gradient. That paper has become like, it's become like everyone knows Amari now. And he said, very honestly, said, I didn't even think it was my best paper. So it's very funny because this one paper of Amari, which I refer to, and he calls it natural gradient, but we are mathematician, and the right name is Beltrami operator. It is the gradient when you have some metric, but okay, whatever. This comes later. Okay, so if you try to read Amari, it's a bit a problem. So you have this and this probability, we understand what it is, and Amari talks about the loss, which is minus logarithm of P, okay? This is not the loss function. So I call it Amari loss, is my name, okay? Because if you read the paper of Amari, you read that this is what he calls the loss function. It is not the loss function, okay? Sadly, for us trying to understand. Now, the correct, the loss function is the expected value. So is the expected label Y given to your probability. So let me try to explain this, okay? So can I use the board for the people that are here? But you guys can see the board. You cannot see the board, correct?
Yes, we can see the board.
So perhaps I should use some other way. Okay. So I'm trying to figure out how to no, because if I write on the board, they will not see it. But if I write on a piece of paper, I don't see the formulas. So this is a very difficult. Okay. All right. Okay. Let's keep it just for a moment. I'll do an example because I want to do an example. But we understand there is something called Amari loss and there is something called empirical loss. For the moment, the two of them look very different. They don't even look at what it is related to us. So let's wait. Okay, so let's make a very explicit example, and I hope this can clarify. Okay, so suppose we have 3 categories: cat, horse, and dogs. Okay, so the very concrete example, and this spits out these scores. Okay, so the first image gives us 5, 4, 2. Second gives you 4 to 8. Third one 4, 4, 1. Clearly, the first, the first score is good because at least cat is bigger, right? So cat is 5, the The other two are kind of bad because a horse is getting 2 and the other get more. You understand the deal, right? How do we record the fact that you have these bad numbers? Okay, first thing, we transform, so the probability of cat, pcat, so I do e to the 5 divided by everything, e to the 4 divided by, so you understand what I'm doing, right? I'm picking the score and transforming it into a probability. And when you transform it by looking at pcat, you say, oh, okay, 71% is cat, very good. 26, what is it, horse, and 4% dog, wonderful. But how do we transform this into a loss, into an error? We transform it by taking the logarithm of this, meaning you take the log of the category of 71. So the logarithm of 0, sorry, I shouldn't, okay, I made a mistake. I should take pcat for the label of cat. So pcat, cat, okay. So is so if you take the minus logarithm of 0.71, you get 0.34, okay? So you are losing 0.34. You understand how this is computed? So I'm sorry, it is not the logarithm of pcat, it's logarithm of pcat, the entry of cat. Okay? Okay, so what is the total loss? We played the same game for everything, right? So the loss will be what we lose for cat, logarithm of 71, 0.71, we get 34, and then horse. Notice that here I took this slide from a computer science person that decided to look at the first two significant figures, and then he's taking happily the logarithm of 0. This makes us feel really, I know it's full of that. If you read their slides, that's a lot. I like it. So, because I do really what you are supposed to do. So I do e to the 4, so I compute this, so I do pcat, right? You can do p horse. So let me show you what you do. So you do I know, I explain. So if you, so in this picture here, if you have, so suppose here we get 4 to 8, right? So you get 4, you get 2, and you get 8, right? So this will produce, so you go e to the 4 divided by e to the 4 plus e to the 8. So this is your p, right? The probability, so you have 3, and e to the 2 divided by e to the 4. And you get from this, you get 3 numbers, which are 0.26, 20. I mean, you use a calculator, of course, 0.26, 0.002, and then what is the last one? 0.98. Okay, you understand how you got it? So you transform it into probability, and these are the probabilities. But the friend here, which I took the slide from, he decided to cut it to the second significant, right? So the 2 went away. Okay, but we compute. And then the important thing is that the image was a horse image, okay? So in order to compute the loss, you pick, so there are cat, so see there is cat, horse, and then what was the other? Dog. So in order to compute the loss, you are picking the probability regarding the category, the correct label, okay? Because it has to tell you whether or not you're doing well. Okay? Right. Yes, indeed. So in that you take only 0.71 for the cat, 0.002 and 0.02. And if you compute, you see this. right? And I mean, I don't have to tell you, but of course, logarithm of 0,002 is a negative number, very negative. So this will give you a big loss. And in fact, this is enhancing the error, right? Because cat, we know 71 is okay, small error, 0.34. But the one of the horse is big error because it's giving you 4 for the cat, 2 for the horse, and 8 for the dog, right? So that's a big error. So you wanted to point this out. For the dog, come on, that's not so bad because what is it? Is no, it's bad. It's bad. Sorry, it's 0.02. So it's 50% cat, 50% dog, 0. So yes, it is 4, almost 4. Okay. So you understand how this is computed, right? Okay. I think true examples help you to understand the madness. Okay. So as I promised last time, I was asking you about the Kullback-Leibler divergence. People don't know what that is. Yes, no, yes. Okay. Being a person that knows very little about these things, so measures the difference between the correct distribution and the empirical one. Let me try to express what is this thing, right? So this is the definition. Great. Okay, let's try to understand what this means. Okay, in the previous example of the cat, so let me, we had here, so it is written there, so it is, we had probability, so we had the score for the cat, so the cat was some score that gave us probability 0.71, that was a cat, and then there was this 0.26 and 0.04, something like that. Okay, so this is it. Now, what is the probability, true probability? Well, the true probability is that you have a cat, 1, 0, 0, right? That's the point. So what are you doing? You are taking the logarithm of this and you multiply by 1. You take the logarithm of this multiplied by 0, so it will enhance that number, right? So the Kullback-Leibler divergence is giving you the 0.34, which is indeed the loss. Okay. So at this point, you may say to me, saying, why, Fioresi, are you making things this complicated? We were so happy with that. No, I think I'm making things complicated because, first of all, you read the things and you read the Kullback-Leibler, and if you're like me, you're like, oh my God, what is it? Okay, so this is the first thing. The second thing is that I'm showing to you that is really what is happening, okay? So these guys are measuring the difference between your empirical probability, Px, and Q of x, okay? What happens if P of x is equal to Q of x? What happens if here you have 1 and here you have 0, suppose? Well, it happens that when you take 1 times log x, sorry, 1, this is Q, right? Logarithm of 1, and then plus 0 logarithm of 0, plus 0 logarithm of 0. That is what you get. So this is Q1, Q2, Q3, and this is P1, P2, P3, okay? So this is what happens when Q is equal to P. When your empirical coincides, and now you may wonder, wait a moment, Fioresi, what are you doing? 0 times logarithm of 0. Why does it work? Why? Go. Huh? No, for another reason. Why this? Because logarithm of 0 is a problem. Okay, but why it is not a problem for us? We are on a computer. 0 does not exist, never exist. So it's a number that is perhaps very, very negative, but then you multiply by 0, and there it is 0, right? No problem, okay? So that is, I know, I asked her because I knew it was her. Is the weak link of the chain. Oh, really? Oh, I am so sorry. I couldn't hear. Okay. Yes, I'm sure. Yes, you are right. Yes, yes, indeed. You are correct. It's a mistake. Nicola, very good. Very good. Yes, there is a little mistake. You have to, yeah, divide by QI. No, you're right. There is a typo. Right. Okay, I show you later. I have another. Okay. Okay, now it is. Okay, it's. Okay, I don't know what to do. It didn't. Oh. You had a clever way to do this before. How do you do this? Yes. Okay. So that's right. That is the that's the definition of the Kullback-Leibler. So this is the Kullback-Leibler. This one. This is KL, right? So it's QI and then logarithm of is okay. Is wait. No, I think. Okay, I will. Okay, guys, let's not worry too much about. I said I was going to say wrong things, and possibly this is where I do them. Okay, I will come back to you next time because if there is an error, I won't be able to catch it now. Yes, yes, they have to do with entropy indeed. Yes, this is Shannon's entropy. Yes, but I didn't want to. Okay. All right. Is somebody knowing? Okay, let's. I just wanted to point out that you can perceive this as a difference between the true probability and the. But did I convince you that our loss function is measuring the error? That's what I wanted in the example. And there is a relation with the Kullback-Leibler. I didn't want to do more. Okay, the click. Okay, then I also wanted to say something brief about the optimizers, which is stochastic gradient that we just said, the descent, and then the stochastic gradient descent with Nestor momentum, and then this Adam that mixes the two techniques and God knows what it does. It's very, so my question for you, my advice for you is that when you're choosing your optimizer, and perhaps Ferdinando that is doing the lab for us will allow you to choose it. I don't know what is, it's like, be sure that you take some time to read the options because there are little numbers that you can play with. For example, there is something called the regularization, and I want to spend a minute of it. It's not such a big deal. So what do? You are adding a parameter lambda that takes essentially the L2 norm because it's Wj of your parameters. Why do you put that? Because so if you don't put the regularization, remember you are minimizing the loss. You are looking at the minimum. This lambda will keep the weights under control, so they will not escalate to become really big. You may not worry about that. You may think, you know what, I'm happy if they're big, true. You can do everything taking lambda equals 0, you are fine. But I'm saying in some problems, if you don't put this lambda, your parameters will escalate, will become really big. And with this lambda, you keep them under control because essentially you are minimizing the norm of that vector. So it cannot be very big, that's all. It's a very stupid thing. And with my student, we were looking at the problem, she didn't put the regularization. Once she put the regularization, something happened. So make sure you try with and without and see what works best. It really depends on what you're doing. Okay, I here wanted to say some words about the Fisher metric. So when we look at the space of parameters, there is this object, which is the expected value of the gradient of the Amari loss, which is called the Fisher metric or matrix, as you prefer. And it's a metric on the space of the parameters. And everyone in information geometry considers this metric as non-degenerate. In deep learning, it is severely degenerate, very degenerate. So the space of parameter is like millions. This metric, we prove it has rank 10, this matrix, okay? So it's not that is like a rank, this is very far. So this is the work by Amari, natural gradient work efficiently in learning. So essentially all information geometry is based on some assumptions that deep learning will not satisfy. So for example, if you're looking at the Beltrami operator, there is the inverse of the metric in front of the Beltrami operator, right? And they're using it. And I point out in many talks, I raise my hand and say, how can you invert the Fisher? The Fisher is not invertible. And they said, that's not a big deal. No, it is a big deal. It is a very big deal that you invert something that's not, it's okay. Why? Because it's never zero, right? This is how they play this game, but it's not the right way to do it. So why it is a good measure, this metric? So first of all, we understand that there is a metric, right? And at the moment you're like, okay, this is a madness. Why define such a thing? I try to convince you. So F is the covariance matrix of the gradient of the Amari loss, okay? So first of all, this is a little bit of mathematics, but very little. So the Amari loss is the logarithm of P, right? P is our empirical loss, right? Dog, cats, whatever. So if you compute the gradient, that's very stupid because you have a gradient of logarithm is gradient of P divided by P. This is like very easy mathematics. And then we notice the expected value of the gradient of the loss is 0. And this is coming from a very simple reasoning because you apply the, the gradient of, the definition of expected value, and then you take the summation inside the gradient. Summation of probability is 1, you do the gradient is 0. It's not smart, it's just a little calculation. Equipped with this, we compute the covariant matrix. What is covariant? Is gradient of the loss minus expected value, but expected value is 0, so you really get the Fisher, okay? Fisher information matrix, you heard that before. So it makes sense, right? So this is, now what you can show, this is a bit more involved, is that the Fisher is the Hessian of the Amari loss, okay? How do you prove it? It's, again, I put this the calculation, but they're really straightforward. You just compute, so you get what our friends, the differential geometry call an Hessian geometry, because the metric F is the Hessian of some function, okay? Here is not really the Hessian of the function, is the expected value of the Hessian. Not so different, okay? Problem is that it is degenerate, that is inevitable. So I couldn't resist the temptation to show to you this little theorem. I have only a few minutes, I won't be able to finish everything I wanted to say, but you can prove, this is straightforward, that the Kullback-Leibler between, so look at this formula. I don't want to prove the formula, which is something not so important, but when the probability varies of a little, you use Taylor expansion is not, you see that the difference between probability at W plus delta W and probability is, evaluated by the Fisher up to some higher order. But this happens when your algorithm is reaching the equilibrium. because when the algorithm is approaching to, the end of it where the loss is the lowest possible, then the probability doesn't change. So P at W plus delta W is like P at W. So probability stops changing. So at that point, the Fisher gives you a natural metric for this space. And this metric is a Hessian metric. The problem is it is not a metric. So with my student Grementieri, we proved that the rank of this huge matrix, right? This, remember, it's the parameters gradient with respect to the parameters. Parameters are 1 million, so it's 1 million times 1 million. If you do it in a short data set, is 1,000 times 1,000, that is huge matrix, has the rank bounded by the number of classes. With my PhD student, Elliot, now we are able to show, which is even scarier, that if you stop at a point where is a data point, it is even smaller. So we put, first of all, we put a bound, like in Cipher 10 is bound 10, but then we even make it smaller. So what are these people in information geometry doing? They're taking it as a metric. Can you take a metric? So you can't take a metric in a 1 million dimensional space that has a rank 10. You cannot. Being a geometer, you know that only two things, you hope two things happen. One thing is that you can restrict yourself to a submanifold where this makes sense, is a true metric, or you can go into the sub-Riemannian game. Now, this is really ugly. You know what sub-Riemannian is? Don't worry if you don't know. We are not going to that game, but she knows. If you go to the sub-Riemannian, that's not good because the bracket doesn't close to a constant rank space. So it is very, very ugly. So it is a situation that is really not good. So I wanted to explain something I did, but instead of going, because I want to leave the floor to Ferdinando, let me show you a picture because, yeah, we have like a theorem regarding application of Frobenius. I don't want to see, this was my, see, I was so happy. Wrote it, but let me give you a picture, okay? So what we discover is the following. We are looking, instead of the parameter space, we're looking at the space of data. Ferdinando is here. Okay, so everything we said before the parameters, you can play with the data. What we discover is that if you try to compute the Fisher matrix for the data, not the parameters, the data, the mathematical formula is the same, you discover that this metric has rank 10, true, is a very low rank, but it is generating, so the gradient of the probability is generating a distribution which is closed with respect to the bracket. Now, you guys don't know what the distribution is? Yes, no? Okay. So this will foliate your space. You know, your algebraic geometry, you know a lot about the Frobenius theorem foliations, right? Not so much. Okay, too bad. So what I'm trying to tell you is that using this Fisher, you can divide your data space into leaves that are submanifolds, and we can prove that there is one of these leaves where all your data is. So you are performing what is called dimensionality reduction, which is very strong because we can navigate the data leaf. And in fact, look how beautiful is this picture. It shows that if you are on the data leaves and you move from one point to another, you stay, okay, they're not all data, but you stay with some, this could be data, it's like a number 8, right? But if you go on a noisy leaf, another leaf, you somehow keep the same amount of noise. That is what we've been doing. So this is as potential application. So this is other example when you move around the data leaf. So I think that I wanted to say much more. Look, if you move orthogonally, you're going away, you start from a point that is data and immediately you add the noise, right? You're adding noise if you go orthogonal. So this is experiments we did. So, but I want to take like a few minutes and have Ferdinando. Yeah, so we did the experiment with Chifa. Right, I wanted to do the human cortex, but evidently that was not it. So Ferdinando, are you here? Ferdinando, I saw you are here. Ferdinando?
Yes. I'm here. Can you hear me?
Yes, we can.
Yes,
we
they can.
cannot hear you. That is very sad. So
Someone-
can you guys wait,
probably she's
Ferdinando,
not
can you
able.
guys connect and perhaps if you connect, we can hear him speaking. You understand what I'm saying, right?
Sorry, say it again because, yeah, okay.
Aspetta. Stai collegando? Perché sentiamo dal tuo altoparlante. Oh. Non so perché non va. A casa andava, ovviamente. So we are starting the hands-on session. So we stop just 2 minutes to set up the equipment. And yes, Ferdinando, I am very hopeful that it will work. So you guys need a portable computer and you need a Colab account, Google account. Ah sì, hai ragione, scusa. Sì, sì. Shannon Entropy. Ah. Ecco. Allora, no, I needed to shut up the microphone.
Okay, can you hear me?
Ferdinando? Ma sei mutato, non ci può sentire.
Yes, I'm trying to speak. Can you hear me?
Yes, I can hear you.
Yes, so from home. Ah, okay.
We can hear you, but
Okay,
probably
okay.
she cannot.
Yeah, well, okay, she's writing, we can hear you. So I assume that she can, and that the people in the room can hear me as well. Hopefully. Okay. She cannot talk, but she can hear. Okay, very good. Then I guess that a good place to start might be, well, by sharing one of my screens. Okay, so, okay, yeah. And so, okay, so now you should be able to see my screen, and then perhaps I can also share this notebook with you. So,
Ferdinando, can you hear me?
Yes, now I can.
Ah,
Yes,
great.
okay.
Okay, can you make it a little larger?
I'll try. So let me just.
Yes, because we can, we have troubles seeing it.
Okay, so I've put on the
That's the characters. Yeah.
the link.
Okay, great.
It's okay. Do you want
Yeah,
it
it's
more?
fine, right? Yes. Okay, go ahead, please, go ahead.
Okay. So now clicking on the link, you should be able to access the Colab notebook and hopefully to open it such that you might see what I'm looking at now. Okay, so please tell me if you have a problem. So, okay, so let me start by, well, telling you something about the Colab environment. I don't know what's the background of the people in the audience, so I'll try to be, well, comprehensive, but I'll also skip a few things. So Colab is actually an environment that you can use to run notebooks and to, well, do experiments without having a powerful desktop with a GPU. And so this is very effective because this is a way that, well, that is very useful to, yeah, I mean, run experiments online, and perhaps using Colab, you can share notebooks with other people. And yeah, so this is very convenient if you don't have your own machine. Okay, so yeah, let me just tell you something about the Colab. So actually, Colab can open any notebook. And so, and the syntax
Ferdinando,
is, yes?
Ferdinando, perhaps the very first thing to do is to tell people that they should download the copy of what they're showing so that they can modify it, right?
Yes,
because they don't know that. So you put in chat
the link.
The link,
yes, as
so
I
you
said,
guys
yes.
should go there and download it to your own computer, and then you modify that one. Otherwise, you're modifying what everyone sees, because
Yes.
it's a sharing thing, right?
Yes.
To be accepted to the meeting in order to copy the link.
I don't understand.
Sorry, say it again.
That's right. You have to get into that. Yes.
Yeah, we are waiting for that.
You are waiting.
Yes.
You guys should tell me that. How bad is the professor? Very
Okay.
bad.
But I did share the correct link, so hopefully you should be able to click on it and to access
It's my
this.
fault, Ferdinando. Very, very much my fault. So they're going to do it now. Ma ditelo.
We need again to can you send again the
Sorry, just to be sure, is it enough if we just click on the link, or do we have to do anything else?
Yes, you can just, yes, okay, I can send you again the link.
Send again, Ferdinando.
Ok, ce l'ho adesso.
È perché l'ha mandato che non l'ho. Cioè, ragazzi.
I sent it on the chat.
Quindi lo devi scaricare. Come non l'ha detto? Ma come vado io come duro? Francesco, aspetta, c'è un altro computer.
I mean, yeah.
Sì.
As Rita was saying, so please download it and make your own copy so that you can play with it. Okay. So were you able to do this? People at home? Or people in Modena? or where you are? Okay, okay. So they're not sure. So yeah, so now, so what you should do, so for example, you can try running these first 2 cells and to check that you are able to do something. You can, for example, well, okay, so now it's running. Okay, so you can, for example, modify here, I don't know, 3, right here 4, that you should be able to see 9 as the result of 5 plus 4. If you cannot do this, then you should